Hello everyone. After understanding the concept of linear equations in one variable, it's also important and inevitable for us to understand the opposite of it. Now, when we talk about linear equations, when we say about x is equal to 2, it really is equal to 2. But how about those values not equal to 2? Those are actually the other side of the story. That's why we need to talk about linear inequalities still. When I talk about linear inequalities, one big difference of it from linear equations is the number of solutions. Again, when we talk about x is equal to 2, we only have one solution. Even if when we talk about linear absolute value equations, we can have a maximum of two solutions. We may have one solution, and there can be no there can be instances wherein there could be no solution. However, if we talk about linear inequalities and say x cannot be equal to 2, you might say 1, you might say 3, you might say negative 1 million, you might say positive 1 million. So if we talk about linear inequalities, the solutions are infinitely many, and you cannot describe nor list, you cannot list all of them, but rather you can only describe the solutions into one. That is why when we talk about if we're going to talk about linear inequalities, we can actually present the solutions in many ways. So in this practice exercise, we are going to talk about expressing this given linear inequality form into the other three forms, namely the solution set, the graph, and the interval notation. So again, since we cannot list the number of the solutions for linear inequalities, even if you will say, just like in number one, x is greater than 1, some of you might say 2, some of you might say 3, some of you might say 500, 1 million, even some of you might say 1 and 1/2, 1 and 1/3, 1 and 1/4. There are infinitely many possible solutions there. So we could express them in these three forms. Number one, in term of a solution set, we are not new with the term solution set because we have applied making solution sets when we talk about linear equations. However, when we write solution sets for linear equations, again, even in absolute value equations, there can be two solutions, there can be one, or there can be none. And the way of writing the solution set for linear equations is by roster form. If you can still remember what roster form is a form of writing sets wherein you will list the elements there. But it's very easy for linear equations because you can only have one or two or none. So there are limited number of solutions where you can list them. Again, in linear inequalities, there are infinitely many and you cannot list all of them. And therefore, we cannot use the roster form. Rather, we need to use the other way of writing sets, which is in the set builder notation. Now, in other references, there are many ways to write in a form of set builder notation. In our first grading, we were able to talk about writing a statement. We could also write our solution set in terms of symbolic form. Do not forget that when we write about solution set, it's actually in this form: set of x such that the statement and then the close brace. Don't forget also that we use x here because the given for number one is x. If this is y, we need to use y. If this is, say for example, a, we need to use a here. But since our given is already in the form of x, we will be using x. We are going to place here a statement which could describe the values here. So again, you might say 2, 3, 500, 1 million, 1 and 1/2, 1 and 1/3, 1 and 1/4. And what are they? They're actually, as a whole, x greater than 1. So in writing solution sets for linear inequalities, simply the easiest, copy this, place it there. And then your solution set is x greater than 1. Or this can be read as set of x such that x is greater than 1. Again, there can be many ways to write this, but I am advising you to do this, encouraging you to do this because this is the easiest way. And anyway, and by the way, amongst the three, as long as you're sure about linear inequality form, this is the easiest form of writing the solutions. Let's proceed to the second form, which is in the form of a graph. A graph is the complete terminology for that is the graph of solutions in a real number line. So we have here this real number line. This real number line, as you can still remember, it extends to both infinities. Okay, so extends to both infinities. Okay, the values might be starting from 1, 0, 1, 2, -1, -2, and so on and so forth. So we are going to shade here the items that are actually solutions as mentioned by the linear inequality form here. But let me just give you the easiest form of our graph. First is the real number line. We are lucky that this is 1. But what if this is 1 million? So some of you might write here in terms of scaling 10, 20, 100, 1000, and so on and so forth. So to make it easier, if it's 1, even if it's 1 million, my advice to you is whatever the value here, make it at the center. Nevertheless, we are not destroying the real number line. Ha? We are just giving a value in the middle. It means the 0 is still here, 2 is still here. But I'm just placing here 1 to make it easier for us. Now, to graph our linear inequality form, we have 3 different steps. I'm going to write it here. Step 1, we need to determine the starting point. The starting point. Starting point. Number 2, we need to determine which direction our graph, our solution set is going to. And number 3, we need to decide on the inclusion of the starting point. Yeah, you need to decide on that. Okay, so all of these are actually given already by our linear inequality form. Let's start one by one. Again, our starting point is 1. It is already given by the value here on the right hand side of your inequality. So if this is 10, therefore your starting point is 10. If it's 1 million, then it's 1 million. So that's your starting point. Whatever you see here, that's your starting point here. So we are going to start here and determine where do we go later. As part of our step 2 direction, it is determined by the linear inequality symbol. It tells us about greater than, and it's pointing to the right. So from here, we shade everything to the right. Shade everything to the right. Do not forget to place an arrowhead because this means it goes towards infinity and doesn't end. That's our graph. And number 3, we need to decide whether the starting point is included or not. And when do we decide that? You have 2 different options. Number 1, try to substitute the starting point in our linear inequality form. So you have 1 greater than 1. And answer the question, is it true? Is 1 greater than 1? If your answer is yes, then it's included. If your answer is no, then it's not included. Here, 1 cannot be greater than 1. Therefore, the answer is no. So the answer is no. So number 1, the starting point is not included. To denote not inclusion, we are going to use an open circle. So here, we're going to use here an open circle. Let me erase here. That's an open circle or unshaded circle. If it's included, we are going to use shaded circle. Okay, so this is already our form of our graph. Again, we started with 1. We go to the right based on the linear inequality symbol, and we found out rather that 1 is not included. But I'm going to add, this is the common graph, but let me add another notation for us to make our next form interval notation easier for us. Okay. There are many references also use this, but in our class, we are going to combine them. Nevertheless, they mean the same thing. If it's not included, we are going to use parentheses. If it's included, we are going to use brackets. Okay, so since it's not included, we are going to use parentheses here. But which of the parentheses? This one on the left or the right? We are going to use a parenthesis that could actually be pointing to the same direction, or the towards. I mean, it goes to the movement goes to that direction. Let me just give you a basic analogy. Uh, if you are familiar with the Dragon Ball Z, in the person of our greatest hero, Son Goku, one of his powerful what you call techniques is the Kamehame wave, or Kamehame wave. That's how we read it. One. So consider this as the power of Son Goku. That's his Kamehameha. It is power. So the hand of Son Goku will look like that, right? Right. So we are going to use this form of parentheses. Of course, if we are not going to use this, that's very awkward. The hand of Son Goku points here, and then the power goes to that one. That's another hint. So again, not many. There are fewer references will use both the circle and the parentheses, or even these two. But in this class, I'm going to require you both so that it would be easier for us to understand the next form. So this is now the complete graph with this parenthesis here. Now our third notation, this is our graph, by the way. This is our graph. The third notation is the interval notation. This is actually designed, this is actually declared by the graph, the shaded portion of the graph. So you need to determine the leftmost value and the rightmost value. When we say about interval, it's similar to this. The age of grade 7 students is 12 to 14. That's an example of interval. The value, the lowest value is 12, the highest value is 14. So similar to this one, we're going to pick two values. The left should be the smaller one and the right should be the larger one. So here, the leftmost value is only until 1. It doesn't reach anymore here. So it's until 1. And the rightmost value is a positive infinity. Because we don't know where does it end, we place here positive infinity. Okay. To complete our interval notation, we need to complete it using parentheses or brackets. The reason why I asked you earlier to use parentheses here in this area is to help you determine that in one, we already use parentheses here. This means that one is not included. Okay. That's why we have the parentheses. This is the purpose earlier. Now, as for infinity, infinity is included because it goes towards infinity. So if it's included, we use here the bracket. Again, for non-inclusion, parentheses, for inclusion, brackets. However, guys, I need to tell you something here. Yes, infinity is included. However, we do not know the value of infinity. We could not measure infinity. We don't know what infinity is. So even if infinity is included, and it should be a bracket because it's included, we are not going to use brackets for the infinity. We need to place parentheses for infinity to denote that infinity is immeasurable and infinity should always open. So this is our interval notation. Our interval is from 1 to positive infinity. You used parentheses earlier for 1, so you use parentheses here. It goes towards infinity. It should be a bracket, but since infinity is not measurable or immeasurable, that's why we are going to use the parentheses still. Now there is a question here. Is it okay for us to interchange the value for 1 and positive infinity? Now again, if we talk about interval, similar to what I have said as an example earlier, the age of grade 7 students is 12 to 14. You cannot say the age of grade 7 students is 14 to 12. Well, it could actually be awkward. Or you might say um, the age, or what you got, uh, the um, the number of times I eat per a day is 5 to 3. It should be 3 to 5. The smaller the value, it should be in the left. The bigger the value, it should be on the right. So if you're going to say positive infinity and then 1, it cannot be. They should not be interchanged because infinity is larger than 1. So it should be on the right and 1 should be here on the left. So this is not similar to your your solution set in the roster form, that you can just simply interchange the elements. In the interval notation, it should not be interchanged. I have discussed a very long process for number 1, but let's just apply the same processes for number 2 and number 3. So for number 2, our solution set is a set containing, let me use the color green, set containing x such that, simply copy, x is less than rather, or equal to -9. Set. This is a set. Okay. That's already, that can suffice it. For our graph, again, it extends to both infinities, the negative infinity and positive infinity. Now to graph, it's okay not to start with 1 or 0. Your starting point is already this value here. So place it in the middle. You have -9. Okay. Let's not use the red so that we could actually distinguish the colors for the graph. -9. The direction is indicated by this. It goes towards the left. It points towards the left. So the graph should go towards the left. Not forget to add the arrowhead, which will mean it goes to infinity. Next inclusion. Is -9 included? So you may substitute it here. -9 less than equal -9. Is -9 less than or equal to -9? Take note that we have this notation equality here. This means this is correct. So how do we determine better without substituting the values to the given equation? Simply look at the inequality symbol. In number 1, there was no equality here. That is why 1 is not included. In number 2, there is an inequality here. There is an equality rather. Therefore, -9 is included because -9 is less than or equal to -9. Now that we are sure that it's equal, so we put a shaded circle at 9. And aside from the shaded circle, we are going to use brackets. And which bracket? We need to use a bracket just like the hand of Son Goku. It proceeds there, which would actually tell us the notation later on for the interval notation. This is our graph. So let's try to come up with an interval notation out from this. By the way, this is the graph. Our interval notation value, leftmost value is negative infinity. Rightmost value until here is -9, comma. Again, you use bracket here. Simply use bracket still. Okay, that's why you use bracket earlier. And since it's infinity, it should be bracket. But again, infinity is unknown, immeasurable. The negative infinity is immeasurable. So we use parentheses. Okay. So we use parentheses because infinity is always open. So as you can see, goes like this. Your solution set refers to your linear inequality form. Your interval notation refers to your graph. And your graph refers to your linear inequality form, which will also mean that your interval notation refers to your linear inequality form. Bottom line, we need to come up with a linear inequality form before we could come up with the other 3 forms. So if you're going to solve probably later on linear inequalities, make sure to come up with a good linear inequality form before presenting solution sets, graph, or interval notation. Let's just complete this with number 3. In number 3, our solution set is a set containing x such that x, just simply copy greater than or equal to negative 1 half. Our graph shall start before we draw the starting point. It extends to negative infinity and positive infinity. It starts with negative 1 half. No need to write other values. Just for representation of graph, it could suffice. The direction goes towards the right because it uses greater than. So it uses again arrowhead to denote that it extends towards infinity. Then is negative 1 half included? You might again substitute if you want to, but just simply look at the symbol. Since it has equality, that means negative 1 half is included. So close it and put a bracket in this form. And then finally, this is our graph anyway. By the way, forgot. And this is our interval notation. Rightmost value, rather leftmost value rather, is negative 1 half. Rightmost value is positive infinity. Separate them by a comma. Infinity is always open. And this one tells us that this is also a bracket due to this symbol here. So this completes our practice exercise A for lesson number 1. So we can represent our linear inequality form in terms of solution set, graph, and interval notation, but make sure our linear inequality form is proper and correct. Later on in practice exercise B and C, we will be applying important properties of linear inequality before we come up with linear inequality form and before presenting it in these 3 forms. Thank you very much for watching. Please practice, practice, and practice. Goodbye.